Welcome to S Chemistry. I'm your instructor Dr. Suhas Gaudi and I will be teaching BSc 5th semester Physical Chemistry course on spectroscopy. Here is the outline. So in this chapter we are going to cover rotational spectrum of diatomic molecules, energy levels of rigid rotor, so by semi-classical principle, and the selection rules. So let's start with some introduction about rotation of diatomic molecule and the moment of inertia. So these two terms are well known with 12th standard uh, physics. So still I'm going to cover this in these slides. So what is meant by rotation? So before that we are going to see what is meant by linear momentum. So linear momentum is denoted by a capital P, that is equal to product of mass and velocity. So where m is the mass and v is the linear velocity. So if you multiply these two, then you will get the linear momentum of particular mass. So which is having mass m. So that can be any single particle, or so this linear momentum will be always in one dimensional. So in terms of rotation, so in rotation you will be having a rotational momentum. So rotational momentum is equal to I and into omega. So here I is the moment of inertia and omega is the angular velocity. So as similar as linear velocity, we here this rotation is taking place in a circular path, that's why we take as a angular velocity. So here I and m, which is correlate, can be correlated with each other. So here moment of inertia is nothing but your experienced mass. So in other word, you can say amount of inertia, that is the amount of torque required to rotate a body or accelerate its motion. So in order to make that rotate, so in angular way, so we require torque. Your torque is nothing but your force. So your force, depending on how much distance is away from the center of gravity, that much uh, force you have to give more. So your distance is, if it's less, you have to give more force. So here, just to rotate any molecules, you require particular force. So that force, uh, to rotate that molecule, you require particular force. So when it will come, that body will come to the particular acceleration. So that is the concept of moment of inertia. So you can understand in another way. So you can consider, for example, a diatomic molecule, in which where m1 and m2 are the masses of two atoms and r is the equilibrium bond length. So the rotating about an axis passing through its center of gravity. So here center of gravity is nothing but your, you can see in this diagram, in this figure, your center of gravity. So between these two atoms like m1 and m2, there are two masses. So in between distance is r. So just to rotate, so this red arrow is nothing but your angular velocity. So if you give particular force, this atom is going to rotate. So these two atoms, if it's rotate, it will rotate along the this axis, this vertical axis, we call it, that is center of gravity. So here, left hand side and right hand side, like respect to r1 and m1 and r2 and m2, the product of these two will be always equal to each other. So that is the center of mass or center of gravity concept. So this is required for this chapter. Now we will see the rotational spectrum of diatomic molecules, like how that atom will rotate and how the rotational spectrum we will get. So from that we will get the energy levels. So that's we are going to see in this upcoming slides. So Now consider the same example like M1 and M2, which has two different masses of two different atoms, and here R1 and R2 is the distance between from center of gravity, this axis to mass. This distance is R2 and this distance is R1. So total distance between R2, M2, M1 and M2 will be R. So this is nothing but your bond length. So now the center of gravity is defined by the equality of moments about it, that is M1 R1 equal to M2 R2. So this will become equation number 1. The moment of inertia I of a molecule is defined as, so for any molecule you can define moment of inertia that is equal to summation of ith particle mass, which is mi into r1 square. So this will be equation number 2. So you can calculate for n number of masses which is related to the which is away from the center of gravity with r distance ri. So where here Ri is the distance between distance of the ith particle, Mi from the center of gravity, that is the mass of the particle. Since the diatomic molecule has two atoms, then we will be having this equation, that is equation number 3. I equal to m1 into r1 square plus m2 into r2 square, that is equation number 3. Now substitute equation 1 in equation 3, that is m1 r1 equal to m2 r2. From that you have to take m1, instead of m1 you have to put that m1 value over here in equation number 3. So you will get m2 r2 r1 plus m1 r1 r2. So this is equation number 4. So instead of m2 r square, so here we have replaced that m1 r1 divided by r2. So it will get cancelled, and so m1 r1 r2 will be there. So this will become equation number 4. So further, if you calculate take out the common factor, that is r1 r2 from this equation number 4, so you will get equation number 5. So r1 r2 into m2 plus m1. Now from figure 2.5, we know R is the your bond distance is nothing but your R1 plus R2. So now uh, put this value in equation number 5. So that is M1 R1 equal to M2 R2. So instead of R2, put this value R minus R1. So R2 is nothing but your R minus R1. So if you put that, you will get equation number 6. Therefore, from that we will get R1 value and R2 value. That is from this equation. Take M1 to the denominator of this M2 R2. So there you can see from this equation from M2. So M2 R M2 into R minus M2 into R1. So if you take out this in one side, so if this minus goes to that side, so you will get all equation in terms of R. So R1 equal to M2R divided by M1 plus M2, and R2 equal to M1R divided by M1 plus M2. So now substitute the above values of R1 and R2 in equation 3. So what you will get? So I is your amount of inertia of your for diatomic molecule. So I equal to m1 into m2 square divided by m1 plus m2 whole square into r square. So plus m1 square into m2 divided by m1 plus m2 whole square r square. So if you make this, so this will become equation number 7. If you expand this and get simplified, so you will get m1 m2 into in bracket m1 plus m2 divided by m1 plus m2 whole square. So these two are denominator is same, that's why we can do addition of above numerator. So that's how we got this equation number 8 into r square. So now this m1 plus m2 will get cancelled with the denominator 1. So here you will have only m1 m2 divided by m1 plus m2 into r square. So this will become equation number 9. So this is your moment of inertia for rigid diatomic molecule, that is rigid rotor. Now what will happen? The whole that m1 and m2 terms, this m1 and m2, what are the mass is there, plus m1. So we will take this whole term as a mu here. That is will become equation number 10. So mu is nothing but we call it a reduced mass of the molecule. So classically the angular momentum, that is L, of a rotating molecule is given by, that is L equal to I omega, we have seen in first slide. So here I is your like similar as a linear momentum, like mass into velocity. So in rotating we generally take the moment of inertia I into uh, omega, that is angular velocity. So this will become equation number 11. So where omega is the angular velocity, and from therefore the angular momentum is quantized. So the quantized angular momentum have this formula in quantum mechanics. So L equal to in under root J into J plus 1, that is J is the rotational quantum number, into H by 2 pi. So H here is the Planck constant. So J can be any integer value like 0, 1, 2 and so on. So this is equation number 12. Now using this J quantum number, uh, you can calculate various energy levels. So to calculate the energy of rotating molecule, so this is the simplest formula. Like in similar case as you can compare this equation into with a linear. So in linear half mv square will be there. So here for rotating molecule you will be having half into, instead of m you will be having I value, that is in I is for moment of inertia into velocity is here angular velocity, so omega square. So that's how this is the energy of rotating molecule. So hence the quantized rotational energy levels of rigid diatomic rotor is quantized. That's why you will equation will become Ej equal to I half I omega square. So same as here. So that is equal to, now we want to make simplify. So multiply I with denominator and numerator on both side, upper and lower. So you will be having this equation I omega whole square divided by 2I. So I omega whole square means nothing but your L. So here the directly you can write L square divided by 2I. So 2I divided by 2I means from here, uh, if you know the energy levels by using rotational spectroscopy, then you can from moment of inertia you can calculate the reduced mass, and so you will be knowing the reduced mass, and then you can able to calculate the radius of the like bond length of the any molecules from equation number 30. So Ej is equal to, you can rewrite that equation. So h square divided by 8 pi square I into j plus 1, so joules. So this will become equation number 40. So where j equal to 0, 1, 2 and 3. So equation 14 is also obtained by solving the Schrodinger wave equation for a rigid diatomic rotor. By rigid rotor is meant a molecule which rotates so that its inner internuclear bond distance does not change during rotation, so that is their assumption. So it is compulsory to express the energy in centimeter inverse, so rather than in joules. It is This is done by dividing energy in joules by hc when we get, hence the total rotational energy in bracket written as Fj is equal to Ej divided by Hc, and that is equal to H by 8 pi square Ic. So J into J plus 1 centimeter inverse. So J is equal to 0, 1, 2, 3, so on. So the rotational energy written as Fj is called the rotational term. So defining rotational constant B here. So B is equal to H by 8 pi square Ic. So Ic is nothing but your moment of inertia. So this term is denoted in centimeter inverse. So we can rewrite that energy levels like F equal to, that is in joules, that is B into J plus 1. So this will come. So where J can be your rotational quantum number, that is 0, 1, 2, 3, that can be anything, any integer. Now we are going to see the selection rule. So in selection rules is given in quantum mechanics also. So here for rotational molecule, so a selection rule is needed to determine the radiative transition between the rotational energy levels, and the rotational transition for a rigid diatomic molecule are governed by the selection rules. So selection rules is always is necessary here because it always determines the radiative transition, like between which energy level to which energy rotational energy levels the transition is happening. So the rotational transition for in this case we are going to go on for rigid diatomic molecules. So the formula is delta J is equal to plus minus 1. So either your rotational energy can absorb any energy from uh, this difference between two energy levels will be plus or minus 1. So that is the selection rule. So only those transitions allowed in which the rotational quantum number change by unity. So that is the moral of the story. So here positive signs refers to absorption and negative sign refers for the emission of the radiation. That is for rotational absorption or rotational emission. That kind you can say. So for microwave spectra, one usually observed as a absorption spectra, so that the operative part of the selection rule is delta J is equal to plus minus 1. For a transition taking place from J to J plus 1, the rotational frequency is given by, that is J to J plus 1, that is equal to B J plus 1 in bracket J plus 2 minus Bj in bracket J plus 1. So that is equal to, you can take here Bj, so here J plus 1 and J plus 2. So this 2 bracket will get multiplied, you will get J square plus 3J plus 2, and the remaining thing will be as it is. So Bj, so here J square and plus J will be there. So if you take subtraction between these two columns, so this will be equal to 2b in bracket J plus 1. So the unit of this is the centimeter inverse. Now from this equation you can calculate the vibrational rotational energy levels from how, if we carry 0 to 1, transition take place from 0 to 1 or 1 to 2 or 2 to 3. So what will be the energy of the in terms of B, that is rotational constant. So here from, if we tell rotation absorption will take place from 0 to 1, you will be having difference, that is 2b. If absorption taking from 1 to 2, you will be having 4b. From 2 to 3 you will be having 6b, and for absorption if you take 3 to 4 energy levels you will having 8b, etc. So the rotational spectrum of rigid diatomic molecule consists of series of lines at 2b, 4b, 6b, 8b, etc. So evidently these lines are equally spaced by an amount of 2b dash 2b bar. So here your j is equal to 0, 1, 2, 3, 4, and 5. So this will be having 2b, 2b, 2b. So here you can say here like 2 to 0 to 2b, that is the first, 0 to 1. Here 1 to 2 means 4b. So difference between 2b to 1b to 2b, that is 4. So that's why 2 plus 4. So here 6b, that's energy level is coming as a 6b, that is bar. This bar is coming, that is because of your unit of rotational energy is centimeter inverse. So difference between 2 to 3 transition is taking place. So difference is 6b. So 6b plus 6b, you will be having 12b. So like that, this rotational energy we have got from the selection rules. So this is only for the rigid diatomic molecule. So here we come to end of this chapter. So these are the references for images and for content. These are the 4 books. Student can refer this. So thank you for kind listening and see you in next lecture. Till then, happy learning.